3 files, combined under 100 lines of Kotlin. They live in core common, the foundation layer that every other module in the project depends on. They are not flashy, no charts, no animations, no data, but every repository, every use case, every component, and every compose screen in this codebase is built on top of them. If you get these wrong, the consequences propagate everywhere. You chase exceptions across the domain boundary. You write fragile UI code that handles error states in some screens but not others. You write tests that require real threads and real timing. If you get them right, the architecture locks in place. Each layer has a single, compiler-verified way to communicate loading states, errors, and data. This episode covers Result, AppError, DispatcherProvider, and safeFetch, the 4 contracts that make the rest of the project possible. Kotlin ships with a std-lib-result type. Why not use it? 2 reasons. First, the std-lib-result has 2 states, success and failure. A data layer that talks to a network and the cache needs 3, loading, success, and error. A 2-state result cannot model the moment after a network call starts but before it finishes. Without a loading state, the UI has to guess. Either it shows stale data as current data, or it hides data that it actually has. Second, the std-lib result wraps any throwable as its failure type. But the UI does not want raw throwables. It wants a sealed taxonomy of failures it can render as localized strings. A network timeout looks different to a user than a 500 error or a malformed response. With any throwable, the UI has to pattern match on runtime types which the compiler cannot verify. With a sealed error type, the compiler verifies every case is handled. Open core command / sac command main /eurostat core command /result @eth. The sealed interface result wraps a single type parameter t declared covariant with the out keyword. 3 variants. Othing is a data object, it has no payload, and it extends result of nothing, which is what the covariant out t enables. Success carries a data field of type t and a boolean called isStale, defaulting to false. Error carries a cause field of type AppError. That is the entire type 9 lines of code, including braces. The covariance matters more than it looks. Because T is covariant, a result of cat is a subtype of result of animal. This is what allows loading and error, which are result of nothing, to be assigned to a variable typed as result of population data without a cast. Loading is genuinely compatible with any result T. The isStale field on the success variant is the secret ingredient for the caching strategy this app uses, called stale-while-revalidate. Here is how it works. When the repository receives a request, it first checks the cache. If there is cache to cache, if there is cache to see, emits a success immediately with isStale set to true. That is 1 emission, then it goes to the network. If the network call succeeds, it emits a second success with the fresh data and isStale set to false. If the network call fails and there was already a cached emission, it swallows the error silently. The UI shows the stale banner from Core UI, but does not replace the data with an error screen. If there was no cache and the network fails, then the repository emits error. The isStale boolean encodes this entire 2-emission protocol in a single field. Every feature module in the project follows this exact sequence. AppError is declared in the same file as result. It is a sealed interface with 5 variants. No network is a data object for when there is no connectivity. HTTP error carries the HTTP status code, and the message string used when the server returns a 400 or 500 response. Parse error carries a message string used when the JSON stat parser fails or deserialization throws. CacheEmpty is a data object for the case where the local database has no data at all. Unknown wraps any arbitrary throwable that does not fit the above categories, usually an unexpected runtime exception. The conversion from exception to app error happens in the repository implementation. Propositories map IO exception to no network, map codes client request exception to HTTP error, map serialization exceptions to parse error. The UI never sees a raw exception. It receives an app error variant and maps it to a localized message string. The key property of a sealed type is that every when expression over it must be exhaustive, and the compiler verifies this. Look at the toUser message extension in population component. It is a when expression over app error, with 5 branches, 1 per variant. If you add a new app error variant anywhere in the codebase, every when expression that covers app error without a catch-all else branch becomes a compile error. The IDE highlights them immediately. You cannot accidentally forget a UI rendering case for a new error type. This is the primary reason we use a sealed hierarchy instead of open exception subclasses. Open hierarchies are extensible but unverifiable. Sealed hierarchies are closed but compiler checked for a domain error taxonomy that the UI must handle exhaustively. Sealed is always the right choice. The same logic applies to the result type. Adding a new result variant forces every consumer to handle it before the build succeeds. Open core common//common main kotlin/Eurostat core common/DispatcherProvider. Interface has 3 properties: main, IO, and default, each of type coroutine dispatcher. That interface is trivial. The substance is in what it enables. Every repository and use case in this project receives a dispatcher provider, uConstructor, EO or dispatcher's default, directly extractor, injection, never dispatcher's EO or default. Why does this matter? In production, the dispatcher provider implementation for Android maps IO to dispatchers.io, the real JVM thread pool. In tests, you replace dispatcher provider with a TestDispatcherProvider with a TestDispatcherProvider that maps all 3 dispatchers to the same standard test dispatcher. That single swap gives the test complete control over coroutine scheduling. All coroutines run synchronously on demand when the test advances the scheduler. No real threads, no real time, no flakiness. The default implementation of DefaultDispatcherProvider uses expectActual, and this is one of the places in the codebase where expectActual is genuinely necessary rather than optional. On Android and desktop JVM, dispatchers.io is a real thread pool backed by Java's executor service. On iOS native, dispatchers.io does not exist at all. The Kotlin native runtime has a different threading model. All Kotlin code runs on a single thread by default, with opt-in multithreading. The actual default dispatcher provider for iOS maps IO to dispatcher, default, which is the nearest equivalent. If you hardcode dispatchers default, if you hardcode dispatchers IO in common main, the iOS build would compile but crash at runtime with a missing symbol error on some platforms. The interface plus expectActual combination solves both the production platform difference and the test substitution problem simultaneously. One interface, 4 implementations, Android, iOS, desktop, and test. Look at the test for population repository in play. Near the top of the test file, there is a class called TestDispatcherProvider. It implements the DispatcherProvider interface directly. No mock egg, because mock egg does not work on iOS native. 3 lines, main, IO, and default all point to the same TestDispatcher instance passed in the constructor. When the test creates the repository, it passes this TestDispatcherProvider instead of the real one. Now all 3 dispatchers are the same controllable clock. The test calls repository.observe query, which internally calls flow1 dispatchers.io, because dispatchers.io is the test dispatcher. The flow does not jump to a background thread. It runs synchronously when the test advances the dispatcher. Turbine's await item then collects the next emission without any real async behavior. This is deterministic, romanistic, repeatable, zero-flakiness testing of production async code. Open core command/sorg command/use eurostat core/safefetch SGF. The function is 12 lines. It is a suspend inline function that runs a block, catches any throwable, reports it via onError, and returns null on failure. There is a single catch clause before the throwable handler. It catches CancellationException and immediately rows it. This is the most common Coroutines bug in production. Kotlin codebases. Coroutines use CancellationException internally to propagate cancellation through the structured concurrency tree. If your error-catching code swallows a cancellation exception, the coroutine does not know it has been cancelled. It continues running after the parent scope has been cancelled. It leaks. On iOS, leaking coroutines that hold references to compose state can cause crashes. On Android, they cause memory leaks that appear in Leak Canary but are surprisingly hard to trace. Rethrowing a cancellation exception is not optional. It is a correctness requirement. Let us trace a complete request from the UI through the contracts and back. The user taps the population tab. The decompose component goes usecase.observe query and collects the resulting flow into its state flow. The flow emits result. Loading first, the UI shows a loading shimmer. The repository checks the cache. If the cache has data, it emits result success with isStale true. The component maps isStale to show the stale banner component. Then the repository calls the API using safeFetch. If the API succeeds, it emits result success with fresh data and isStale false. The banner disappears. If the API fails and cache was already emitted, the error is swallowed. If there was no cache and the API fails, an error with an AppError variant. The component maps that AppError to a localized string using an exhaustive when expression, shows the error state composable, and offers a retry button that triggers a new observe call. 3 types and the 100 lines combined, and every feature module is built on them. Result gives the data layer a 3-state protocol: loading, success with staleness, and typed error that the compiler verifies at every consumer. AppError gives the UI a closed, exhaustive error taxonomy it cannot accidentally miss. DispatcherProvider gives every repository the ability to be tested deterministically without real threads. And safeFetch ensures cancellation exception is never swallowed, keeping structured concurrency intact across all platforms. Get these 4 right at the start of a KMP project and the architecture holds. Skip any of them and you will re-implement them under pressure inconsistently across 9 feature modules. The next episode goes deep on Ktor and how the single shared HTTP client is wired to 2 different engines through the expect actual mechanism we saw in episode 2. Subscribe for more on Android AI tooling and Kotlin multiplatform.